Okay, so let's look at the pH of a buffer solution. It's assessment statement 18.2.2, solve problems involving the composition and pH of a specified buffer system. Now, I covered the composition of a buffer system in my previous video, so it's better if you watch that first before trying this one. Okay. So, from the previous video, we know that an acidic buffer is made of a weak acid, which we're going to call HA, okay, and its salt, which we're going to call MA. Now, there are some assumptions that we make, and I'm going to cover those now. So, we assume that the dissociation of the weak acid is so small that the concentration of the acid initially is equal to the concentration of the acid in the equilibrium or final. Okay. The second assumption we make is the salt Ma is fully dissociated. So the concentration of the salt is equal to the concentration of the A negative at equilibrium. Okay. So let's just see what we mean by that. Here's a problem which we'll try in a minute. Calculate the pH of a buffer solution at 298 K. And we're mixing 25 centimeters cubed of 0.100 mole per decimeter ethanoic acid. Okay, so there's our weak acid, and 25 centimeters cubed of 0.100 mole per decimeter of sodium ethanoate. So there's our salt. Okay, so what we're going to assume is the concentration of the HA, the weak acid, is the same as the initial, so which gives us 0.100 mole per decimeter, and the concentration of the A negative, or the ethanoate ion, is going to be 0.100 mole per decimeter. Okay. Now we're going to have a look at the equation that we're going to use to calculate the pH of a buffer solution. It's called the Henderson-Hasselbalch equation, and you have to know this. Okay. There's two kinds. There's one for pH and there's one for pOH. Okay. So it's pKa plus log of the salt over acid for pH, and pKb plus the log of the salt over base for pOH. So let's try an example now. Calculate the pH of a buffer solution prepared by mixing this quantity of ethanoic acid and that quantity of sodium ethanoate, and we're given the Ka of ethanoic acid. So we're going to use the Henderson-Hasselbalch equation for pH, obviously. Okay. Now we're given Ka, but you have to input pKa into the equation. So what you need to do is this: you take the negative log of the Ka. Okay, so there's our Ka, which is 1.8 times 10. Okay, the negative 5 should be up there, plus the log of the concentration of the salt over the acid. Now remember, the assumption is that we use these concentrations in the equation. Okay, so if we do the math on that, negative log of 1.8 times 10 to negative 5 plus the log of 0.100 over 0.100, we get 4.74. Okay, now the point is here: if the buffer solution contains equal amounts in moles of acid and salt, or base and salt, the last term becomes 0. So what we mean is, if we have equal number of moles of the acid and the salt, like we do here, equal number of moles, okay, this is moles, then basically the last term, which is this term here, that becomes 0. Okay, so we could have just said that the pH is equal to the pKa. Okay, and the pKa, of course, is the negative log, this part here. Okay, so we could just take the negative log of 1.8 times 10 to negative 5, and that would give us 4.74, which is the pH. Okay.